notion. So today we'll talk about compressed. We'll talk about compressed sensing and an approach to actually solve the compressed sensing problem called orthogonal matching pursuit. That's what OMP stands for. Okay, so many people have heard of compressed sensing. Heard of this term before. Okay. So cool. So this is kind of a neat technique that's only. So this is a technique that solves something very similar to like to doing like ordinary least squares for linear regression. But so like least squares goes back. Maybe goes back to like Gauss or like Legendre or like some people like that. It's a very classic technique. This one is maybe like, this was only like maybe like 10 or 15 years old. So it's a kind of a brand new way of looking at these problems. And so I'll try and write kind of a version of the problem down and you can see how they're similar. And you first may think, okay, this is not possible, and then I'll hopefully by the end of the lecture I'll change your mind on that. So, okay, so if you're doing least squares, so if you remember the least squares problem, so least so least squares regression, the idea was that there's some matrix A, which is going to be like n times d, and then there's going to be some unknowns x, and you want these to approximately equal a matrix B, which is going to be n by 1. Okay, and so the matrix X is going to be 1 by D, I think, and so you can, and the least squares solution is the arg min X of AX minus B. You can write it as squares here, right? So you want to find the x so that you multiply x by a, and you're going to get a vector, and length that vector that looks like b as close as possible, minimizing the sum of the squares of all of the differences of this. And this makes sense when n is bigger or equal to d. In that case, you can solve for x as A transpose A inverse A, probably, it's not quite right, I might be mixing up the transposes, but there's kind of some solution for this. You can write this down. And this works because n is bigger than d. Basically, if you remember from your linear algebra class, basically what you're doing is there are going to be these. So x is going to have these d unknown variables, and there's n linear equations that are describing these variables. And so you can find the kind of the best set of d things that fits this as well as possible. You're going to have some error. You're not going to be able to hit this exactly. What happens if d is larger than n? This is d by 1. What happens if d is larger than n? Yeah.
Then you've got an under-constrained system, so you can't solve for the x. Or is it the other way?
Well, so if d is equal to n, you can solve. There's exactly one x. If d is less than n, then you can't solve for x, so the error is 0. So you solve this that has the smallest squared error. Okay. So if d is bigger than n, then there are so many solutions to x with zero error. Okay, there's zero error. You can solve for an x so that this error is 0. So there's not one minimum solution x. Okay, so you can do, you can actually, you can use like Gaussian elimination in some way to solve for this. Okay, so from a data perspective, this seems, it should be strange. You should think of the n as the number of observations. So these are the observations, and these are the variables. Okay, so there are more observations than you have variables. If you have more variables than observations, well, you can fit variables to fit your observations, but you can have leftover variables. Who's to say that you got the right variables? What we care about is making more and more observations and get a better and better approximation of the variables. And figure out what are the right variables. We want to understand what is the right model here. And so if there's many solutions, if D is bigger than N, there are many solutions to our model. Which means we're not really saying what is the right model. We can give a subspace of all of the possible right models. So that's somehow not useful or interesting anymore. Okay, so how do we choose the right model if there are many right models that all give us no error, saying there was no noise in the data? That somehow doesn't make sense if there's no noise in the data. Okay? So So if you took most linear algebra classes, they'd say if n is bigger than d, this is going to be bad because you can't solve for x. But in a data mining class, you're doing data analysis, you want n to be much bigger than d so you can solve for x, that you know if you add more data, you're going to get a better understanding. Each thing kind of is going to add to the noise, add to the error term, but on average, the error is probably going to get better. As you can see, another data point is probably going to fit this model. Okay, so this kind of notion of the number of observations and variables is seeing I'm getting a kind of a strange form of feedback.
Is it kind of like if you just have like really high dimensional data, then you'll likely have less like data points than you will like dimensions sort of thing?
Yeah, so let's give an example. I think, so let's say that I want to build a linear model, so I want to solve for x. That's saying something like, so I want to predict, so I'm giving information on all the students in the class, and I'm given, so let's say there are 80 students in the class, and each of you I've been given like 200 pieces of information about your background, your height, your age, what the circumference is of your ring finger, all these strange things. And so I'm trying to predict what your grade is at the end of the class based on all these strange properties, okay? And so the B is going to be the grade at the end of the class. So I'm trying to predict. Okay, and so I could go back and take your data at the end of the semester, and all the A is saying, this is your data, all the measurements I have about you. And B is your grade at the end. And X is the model. How do I map between the measurements and the grade at the end? And so if I'm trying to, and if I have a model that exactly fits your, that exactly predicts your grade based on things like the circumference of your, ring finger, that shouldn't really have anything to do with it. I'm probably overfitting. I'm telling you your grade exactly based on things, they shouldn't have anything to do with each other. Maybe I picked the wrong variable, it just happened to explain something. If you have so many variables, some of them are not going to be useful. Okay? There should be a simple explanation for what's going on. and I've made it probably an overly complex one. Okay, so the point should be, as I should get the perspective, as you get more observations, as I get more students who I'm getting these measurements, I should be able to do better. So which means I should be doing worse in my modeling if I have fewer observations. If I made this prediction based on one student, I'm probably, when I see another student, I try and take the same measurements and predict their grade, I'm probably going to do worse. Okay, so some of these arguments we'll make a little bit more in the next couple of lectures as well, about kind of the idea of having more data points helps you predict and understanding the noise and cross-validation. But yeah.
Is there like a general, is it, in general, like if you have a lower dimensionality, will you be able to get a higher, like a better regression?
So what's going to happen, and this will be next week, Wednesday, we'll talk about this, and also next week, Monday, it's going to generalize better to new data. So if you've taken the machine learning class, you measure the generalization error. So you're saying, if I got new data, how well do I think I'll do on the new data? And that's really how you should be evaluating this. And so, but I'm just using the data, this is just the data I have. So I'm getting 0 error on that. I'm not going to get 0 error on new data. I'm kind of fooling myself here. Okay, so in compressed sensing, on the other hand, we're going to be talking about this regime where D is bigger than N. And we're going to come up with solutions which actually generalize well, which actually are going to work well. And so I was hoping that this regime would seem strange and like you couldn't possibly do something. Because people in data analysis, when people started solving these problems, they were very surprised that you could find a good model that was essentially using all of your data and did better with more data, but it worked in the regime where D was bigger than N. Okay, and so it's going to look like this, except it's going to have the property that, so in sensing. So in compressed sensing, you're going to have the assumption that X is going to be sparse. Okay, so you're going to have a lot of variables, but you're going to require that your model most of them has a value of 0. And so that's how you're going to get around this. You're going to have lots of variables you can use, but you're going to enforce that a lot of them you can't use. You can only use a small number. So you can make a model that's going to have a lot fewer actual variables that it uses than N. The number of ones it's going to use is going to be much less than N. So you're going to have M much less than N, so non-zeros in X. Okay, so I'm going to solve for this model X, and the number of non-zeros is going to be much smaller than the number of observations. And by doing this, I'm still going to get something that's going to work and it's going to generalize well to new data. So I'm still enforcing my model is small even though I have lots of variables. Okay? And so this is basically like a new technique. I guess there were kind of two groups which have some history between them. So there's kind of 2 papers. I think this was published around 2003, 2004, or one of these may now have been published. So there's one result by Tao and Candace, and then another one by Donahoe. And so so Candace was Donahoe's student, I believe, but several years before this. And Tao, this is actually Terry Tao, who won the Fields Medal for completely other stuff. So this happened around 2004. These compressed sensing techniques came out, and so let me rewrite the system in a way that matches the notes. And so it's going to come at this, and this is mainly came out of the world of signal processing and statistics. So we're going to start where the model, which was X, is going to be S. And we're going to think of this as a signal. And so we're going to say that this is a sparse signal. And so when I first introduce this, I'll talk about this in the notion of bits. It'll be a little bit easier to see the general model, and then we'll talk about an algorithm that'll work on things that have real values instead. But so my S is going to be something that looks like 0, 1, 0, 0, 0, 1, 0. Okay, it's going to be this vector. And this is my model, what I want to recover, or some signal I want to be able to define based on observations of this data. It's going to be a string of bits. Most of them are going to be zeros. There's going to be some of these ones. The ones are the interesting one, right? The ones are telling you what's actually happening. Okay? And so the signal is what I'm hoping to find. So in order to access the signal, I'm going to have some measurements. Okay, and so this measurement is going to be a matrix. So and I guess the length of, I'll say the length of S is going to be this goes from the length of S is going to be D. And so I'm going to get a measurement matrix X. And this matrix is going to be, let's see, it's going to be M by D. Okay? And so this measurement matrix X, each entry, Xij, so this is an entry. So each entry in X is going to have, in this case, a value in -1, 0, and +1. So each of the elements of this matrix is going to have -1, 0, or +1. And so then I'm going to get, so this is, I guess, is the measurement matrix. And then I'm going to get out, let me call this something else. This is, well, let me write this. So this is the measurement matrix. So it's not the measurements. The measurement, which I'm going to see, is going to be X transpose S. I mean, this is X S transpose. Let me get this right. It's XS transpose. XS transpose. So these are going to be the actual measurements. Okay, so I'm going to get actual measurements out with the measurement matrix. So I'm somehow going to have a signal, and if I think of it as a signal processing person, there's something going on in the world. I'm going to measure it some way. That's going to end up being with this matrix X, and I'm going to get out some measurements of here. And so Y is going to look like a vector of size M. So I'm going to get, so this is going to be M by 1. So I'm going to get M measurements out. These are going to be some, these are turns out are going to be some real, in general real values, but these, Y is going to be some integers in this case. So these don't have to be 0, 1 like the others. And so if you think about this a little bit more kind of at one level of this matrix, if I look at a measurement row, let's go through an example. Row, let's call this xi. So this is the ith row of x. So this is going to be, so I'll say xi in my example, maybe this is going to be 1, minus 1, 0, 0, minus 1, 0, minus 1, 1, 0, and so on, right? So these are minus 1s, 1s, and 0s in this case. And so it turns out you're going to want to pick these values at random. And so then in order to get yi, so this is the ith measurement, there are m measurements, I'm going to get the dot product of, I guess this will be xi transpose s, which is the dot product of xi and my signal s. So when I do this multiplication, it's basically I'm taking the dot product with each row by s, and that gives me one of the elements of y. Okay, and so this dot product, if you remember what the dot product is, I have these two vectors, xi and s, and I'm just going to sum up the contents here. Right, so the first one is going to be 0, which comes, or let's write xi first. So this 1 which comes from xi times the 0 which comes from s, plus minus 1 which comes from xi, and the 1 which comes from s, plus 0. So the next term is 0 and 0, 0 and 0, minus 1 and 0. So I'm going to get 3 zeros. And then again, I'm going to get, let's see, a 1 and then this other minus 1 here. So minus 1, 1, plus zeros. And this will just keep going. It'll be a sum of all of these entries here, these D entries. And in the end, this measurement will be something like, in this case, is a minus 2, up through what I've seen so far. Most of the terms, I can completely ignore that these are all zeros. Right, and the only ones that matter are the minus 1 here and the minus 1 here, and they sum up to minus 2. Yeah?
What if you measure something that isn't an integer?
Well then, so let's say in the signal it was not an integer, it was 1.3, right? Then yeah, so then it's going to be a minus 1 times 1.3, I'll get minus 2.3 here. And so then this is not going to be an integer, that's going to be fine.
So
I just want to show an example with just bits first. It's a little bit cleaner. Yeah. Okay, and so I'm going to get these measurements m, and so this is going to be the setting where my claim is I'm going to be able to recover the signal where the number of measurements is much less than d. So I'm going to say m is going to be much less than d, and I'm going to be able to recover s exactly. Recover s exactly. Okay, and so if I have the number of measurements is small, so in this case there's one ground truth s. This is my model, and I'm going to be able to exactly recover this s. But even though there are d measurements, d might be large in this case, right? The number of measurements I need is much less than d. So if I were to check each bit individually, I'd need d different measurements. I could set up this matrix X So the first row was 1 and all zeros. The second row was 0, 1, and then the rest zeros. And each time I learned one of the bits. Okay? And then I could exactly recover S by doing this. Does that make sense? But I'm going to use a number of measurements much less than D, much less than number of bits. And because I'm going to assume that it's sparse, I'm going to be able to recover it. So in general, M is going to be equal to some constant K times I screwed up my notation here. So let's say the number of non-zero is going to be S. So S will be the number of non-zeros. And this is slightly different in the notes, I'm sorry. So the number of measurements I'll need will be K. Some K is going to be an absolute constant times S times log of D over S. Okay, so K is going to be somewhere between 4 and 20. Okay, so the number of measurements I need is going to be about the number of bits that there are, the non-zero bits that there are, with some extra log term here. Now, if I think of the log term in terms of from a computer science perspective, I actually need this much space just to tell me how to index into that array. This tells me the location of each, could tell me the location of each bit. If I were to store this array sparsely, I wouldn't store it as an array of size D, I'd store it as a location of each bit. And then I would say it's S log D, but I can be a little bit smarter. I can just store the gap in between the different bits. And then you need S log D over S. And so that turns out to be the number of measurements you need as well. So it's really, people figure out how to do this. And so the value of K you need here is going to depend on, once you get these measurements, how do you go and get the bits? What algorithm do you use to go back and get the bits? We're going to talk about a technique which is not optimal. It's probably going to be closer to the 20 range here. But there are techniques that can work up to extra factor 4 bits that are more beyond what we'll cover on the class. Okay, so does this kind of makes sense a little bit here? We're going to have this sparse signal here, which is mainly zeros. And then we're going to make these random measurements. We're going to, essentially this measurement matrix, each row is going to be random 1s, -1s, and 0s. And then we're going to, each of those we're going to take a dot product with each of those rows with the signal, and we're going to get out this measurement value. Right? In this example, we'll say -2 here. And then from these measurements, and from knowing the measurement matrix, I'm going to be able to recover the signal exactly, even if the number of measurements is far less than the number of actual locations of the bits. Okay, so this probably seems okay. So what do people think about this problem? What is, does this make sense? Does this sound like a worthwhile thing to study or to talk about in class? Hopefully, maybe. So let me give a couple of examples of how. I'll talk about this bit example because it's easier to kind of define the problem. But there are these examples where people have used this. Examples of compressed sensing. Where have this been used? Well, one of the first kind of physical demonstrations of this was what was called a single pixel camera. And the idea was that, so if you think of these cameras nowadays, they have like these 10 megapixels or even bigger. And if you think of if you look at these telescopes, they have even more megapixels than this. But typically after you take a picture, you're going to compress it into a JPEG or something like almost immediately. Oftentimes, unless you're shooting in RAW, this is done in hardware on the camera, right? So you're taking 10 so 10 gigapixels. Is that the right number? I don't know. And you're going down to a this compression down to JPEG, and that'll be the equivalent of about 2 gigapixels, sometimes much smaller. Okay, so you're doing this compression, and this is before it gets stored in the memory card on your camera or on your iPhone. It's doing this in hardware. So what if I just took measurements equivalent of these 2 gigapixels? Could I get back the same image? That'd be a better way to use the sensors on the camera. So, okay, so this is kind of the idea. This sounds very cool if you could do this. Now they don't actually do that. What they do is they set up a camera that has a single sensor. Think of instead of 10 gigapixels, that means you have, I don't know, it was millions of these individual sensors on this big grid, and each one senses light individually. You have this one sensor, and you just take the value there, and then you have this strange filter here, which is either a +1, a -1, or an occlusion, right? This occlusion is the 0, the -1 is the -1, and the +1 is the +1. Actually, it's just occlusions or non-occlusions, and then they change it to -1s and +1s by averaging them to some way. There's some way to do a conversion, but think of occlusions or non-occlusions. So randomly, it masks what's coming in from the picture, and so then this sits in front of, say, someone standing here, right? And so what you see is some single gray value. And each occlusion mask is one row. All right, so this occlusion mask is going to be one row. And so then they take a picture with this occlusion mask, then they change it to a different occlusion mask at random, and then they take another row. So they only need one pixel, but they take many of these pictures at once. Or maybe they take them over a short period of time. And then the hope is that they can recover this. They can recover the data. Or maybe they have the data coming in and it's running through multiple masks. Each one goes to a different sensor. There's some variations on this. This is kind of a proof of concept. And so they built a camera like this, and it kind of worked, but it doesn't work as well as your regular camera to the JPEG conversion. But you can actually recover something that looks like your picture by doing something like this. So where would this be useful? So if you're looking at the Hubble Space Telescope, at some point I thought I'm not sure they actually did this, there was some hope at least, and maybe they did, but this Hubble Space Telescope is this satellite that has a big camera on it outside the Earth's atmosphere, but it takes a lot of energy for it to send the data back down to Earth. So it takes, in theory, it could take these compressed measurements and then Earth could sort it out where they have more processing power. Was some hope at some point. Where I know this is actually used is doing MRIs, and specifically doing these on kids. So this MRI is like it's like trying to understand whether you have cancer or not. And the thing is, you often need to sit there for a long time, and they take these measurements from these different angles, and it's more complicated than what I described, but it takes, you have to sit there for like 20 minutes, and you have to sit still, otherwise all the different measurements they take don't line up very well. But kids are very squirmy. They have trouble sitting still for a long time. So if you could take fewer measurements and still recover images of the same resolution, then this is really cool. And so this compressed sensing is used in these MRI techniques on kids. They don't take like a grid of different views of you, but they take all these random linear combinations of these different views. And they're able to recover things with much less time, maybe like 1/3 of the time of the regular image with fairly similar spatial resolution. So this is kind of one success of this. Okay, and so there are various other places where these techniques show up inside of other data analysis routines. But these are some concrete ways that this technique is famous for. But now something like a large fraction of signal processing looks at these compressed sensing techniques. And so hopefully we'll see that there's a lot of similarity with some of the things we've been studying in class. Okay, so I guess the question is now, given these measurement and measurement matrices, how do we recover? Given the matrix X and the measurements Y, how to recover S. Right? So if we did these measurements where each row X measured a single pixel, or measured a single bit at a time, it's simple to recover. We knew each row corresponded with 1 bit. Now these things are all jumbled together. Right? Each matrix, each row is kind of mixing up all of the bits together into one value yi. So each row xi jumbled together all of the bits into one value yi. So how do we recover S from this information? Right? And so now now we're in this regime where D is much less, the number of measurements is much less than the number of bits in S. So we can't use these squares approaching, because we don't have enough measurements. Yeah.
Is that X like A and then Y like B?
Yeah, right. So let me translate. This was like the this is like the data. This Y was like B. This is what we're trying to predict, and this X is the model. Right, good. So we're trying to recover the model from the data, or in this case, this is the measurement matrix, how we measured it, and this is what the actual measurements were. Okay, so think of, again, these were your previous students in my class where I had their final grades, and I had these ways of collecting data about them, right? And maybe I took like the circumference of the ring finger, that probably doesn't matter. So instead of that, I'm gonna take like random weird measurements, random combinations of all the possible attributes I have about them. I'm hoping some of those attributes are useful in predicting the grade. Now, the idea is that I should only need a small number of things that are useful in order to predict the grade. I don't need all these superfluous things. Those are going to get zeros in the model, right? The measurements that have nothing to do with the prediction are going to get zeros, right? Okay. So instead of trying to solve for kind of this best fit, I want to pick out the things in the model, or this vector S or X, that are non-zero. So how would I do that? Okay, so we're going to use a technique called orthogonal matching pursuit. And so it's going to be just about the simplest thing you can probably think about here. I'm going to pull out elements of S one by one that I think are doing a good job. Okay, so I'm just going to pick the bits which seem to be helpful. Okay, so let me. So it sounds easy to say, right? But how would I implement that? How would I write that down? Turns out it's simple, but I'll write down the notation for you. So the first step is I'm going to find this column of X. Right, so let me write a picture here now. I'm going to have the signal, or this is going to be Y. This is the measurements I'm getting out. I'm going to have this matrix X. So this is this matrix X. And I'm going to have the sparse signal S here. Okay, and I'll write it this way. I'm actually multiplying. This is Y equals X S S transpose here. But you should really think of it, the bit here affects each of everything in this column into Y. Right? So if I want to understand one of these bits of S, let's say there actually is a 1 here, then everything in this column of X is going to map onto something meaningful in Y. Right? So everything in here, these are the -1s, +1s, and 0s. If it's not a 0, it's either going to add or subtract 1 from Y. If it's a 0 up here in S, then it's not going to do anything. I can ignore those whole columns of X as it turns out. Now, I didn't know that ahead of time. So the first thing I'm going to do is I'm going to try and choose these columns of Y of X. So choose column of X that's most useful. Okay, so what is this going to be? It's going to be, I'll say Xj is going to be the arg max of Xj and X. So this is going to be a column of X. So the column of X, the jth column, which maximizes the inner product of Y and Xj. The magnitude of this inner product. Okay, so if I have a column that the dot product with Y, the magnitude is large, then probably this column is highly correlated with Y. That means there's probably a large value in S here. If there's -1s and +1s in this X and they don't line with the -1s and +1s in Y, then probably it didn't have any effect on Y. They probably balance each other out. That probably means that there was a 0 up here that didn't really do anything. Most of these columns are going to be useless, so the ones which are correlated with Y are probably correspond from a 1 in the signal. So I'm going to find this column, which is going to be this correspond most with Y, and then I'm going to set it to be a 1 bit up here in S. It starts with all 0s, then I set it to be 1. Okay, I'm basically just going to repeat. I'm going to describe it a little bit more. I'm going to describe it as if the algorithm in more detail is if the signal is mainly non-zeros, but some of these values don't have to be 1. They can be other larger values. Okay, so in that case, you can't just put a 1 up there. The next step is going to be to find the best guess of what is in that value Y. So I'm going to set a gamma is going to be arg min Y minus xj gamma. Okay, so I'm going to find the value gamma such that if I multiply this value gamma by this column xj, right, so this is this is xj, that it's going to be as close to y as possible. All right, so what possible value gamma could I put up here? So gamma times xj looks like y. I'm going to solve for that value gamma. This is a convex function. I can solve for this easily. Okay. Okay, and then the final step is I'm going to create so this thing called the residual. This is going to be y minus xj gamma. So then sj gamma. Right, so I'm going to set this value, the jth bit of s to gamma, and then I'm going to take y and I'm going to remove the effect of this column and this value. And I get back this residual, and then I'm going to repeat with y equals to r. Okay, so now I'm going to go back here, and I'm going to again choose the best column, but instead of using the original y, because I'd get back the same column again, I'm going to use r, everything that hasn't been explained yet. Okay, and then I'm just going to repeat this until I've explained as much of what was in y as possible. This residual goes to 0. You know, eventually at some point, if I choose all the correct bits, then this residual is going to be all zeros, because I've explained all of the values in y with the proper bits in s. And at that point, I'm done. Okay, so then you're going to repeat until r is so all zeros, or say r is say small enough. Oh. Let's go. There we go. Yeah. So and this is the whole algorithm. This is orthogonal matching pursuit. So it's just a simple greedy algorithm. I pick one column at a time that's explaining the most. I figure out the best effect of that column, the best value to put in S that explains it. I subtract off the effect of that column, and then I repeat. Okay, so this is pretty simple. And in fact, if the number of measurements is large enough, it looks like some constant times the number of actual non-zero bits, this will actually recover it exactly. Under certain conditions, this will work well enough. Now, the data sets are going to be fairly large, where you actually start seeing this effect, because you'll get like this, maybe a constant 20 in front. But if you start with something with like a million bits, then you could, or a million bits and only 100 of them are ones, then you get like 2,000 measurements, and you can recover these. Maybe it's like 5,000. So much less than the million bits that you have. Okay, and so these actually work well in various settings. You need to scale them up. Okay, so I'll go through an example of this soon, but I want to add a few comments on first. Any questions about how this works yet? Okay, it's pretty simple. So one thing that we'll see, this will mix in with the lecture next week, is it'll sometimes be useful to add what's called a regularization term here. Okay, so to solve this with some regularizer parameter, alpha, to be greater than 1, and some penalty, this will make sense to be, I mean, gamma is a scalar in this case, but we'll see why you may want this to be a non-generalizes. But so you have penalized large values of gamma. When you find the first thing, you'll tend to say, well, you'll tend to kind of over-explain stuff with this. So what you want to do is to penalize large values of gamma. So you tend to choose something that's slightly smaller than what you would have wanted. If you come back later and there's some residual which you didn't explain because you choose gamma too small, you could end up choosing that column again and then give a larger value of gamma because it will match it exactly. Okay, and we'll talk more about these regularization terms on Monday. Okay, but this will actually make this more robust. Something else you can do is that on the second round through here, or beyond there, so instead of instead of saying you can find some, you can try and so in the let's call this in the teeth round, what you're going to have are these columns xj1, xj2, up to xjt, which you've found so far. Okay, and you're going to, and then instead of solving just for a single gamma, what you want to do is to solve for this vector gamma 1, gamma 2, up to gamma t, which is the arg-min of gamma now in RT, such that y minus xj1, xj2 up to xjt times this full gamma is small. Okay, so I can solve, every time I say, I know these t columns, say t is 3, the first 3 columns I have, I know these are the 3 columns that are going to be non-zero. Instead of fixing the previous choice of gamma in the first t minus 1 columns, I'm going to say, let's find the choice of gamma. The choice of gamma, which best captures y altogether. I can go back and revisit the old values of gamma I had before. Okay? And if I do this, I can do even better. Why is this? Oh, that's R to the t. Okay, yeah. So I can do better if I solve for all these at once. This takes longer. How would I solve this problem? So now, before this was like, you can basically write that it's that one's going to be, that one's simple to solve for. It's actually, you can do, so you can solve for this one. Gamma is going to be equal to, what is this going to be? Probably will get this wrong, but I think it's going to be xy transpose over this, because these are xj's. There's going to be this closed form solution for this here. Okay, so x is a vector. I think there's going to be there's a closed form solution for solving for gamma in this case. How can I solve for gamma here? Well, this is now a least squares, well-formed least squares problem again. Because now the number of variables I'm solving for is less than the number of measurements. T is going to be less than the number of measurements I made. T will be less than m. the number of these measurements. So I can again solve for this using this least squares approach. It's going to look just like that, but written in matrix form. Right? So now gamma is going to be x, j, transpose, x, j. This is inverse x transpose y. Right, so I can solve for this in a closed form. But again, probably what I'm going to want to do is actually, I'm going to add, again, this regularization term where I want to penalize gamma for being large, all coordinates. What I haven't specified yet is now this is not just a value, this is now a vector. So I want to say that this is the 2 norm and this one is the 1 norm. It turns out that if you use the 1 norm here, and we'll talk about this on Monday, this will bias towards a sparse solution for gamma. So it bias towards things where some of the gammas are going to be 0 if I can set them 0. So even though I chose some of these columns, maybe I want to go back and say, I didn't really need that column. And so if I use this term here, I'm going to tend to solve for values gamma, which are some I'm going to replace with 0 if I shouldn't have chosen them in the first place. Now this, when I have this L1 regularizer, it's going to be a little trickier to solve, but there's still a way to do it, and we'll just mention that on Monday. Okay. Okay, so this is what I wanted to add. So in practice, you probably replace this solving for gamma with this step inside of here. Right? This will work better. Okay, so let's try and go through an example. Right? This is kind of foreign. And so at the same time, if you haven't seen Matlab, hopefully I'll let you see something here. Hopefully this is going to work. All right. So did everyone see? This is it'll keep moving up the screen. But so this is going to be. Is this big enough? Can I make this? Okay. So here's my signal S. It's some sparse thing. I think I've got 10. D is 10. I've got only 3 bits here. Okay, and so then this is my measurement matrix X. Okay, and so then Y is going to be X times S transpose. So if you haven't seen Matlab before, I've got a matrix. You can store it natively as a matrix, and you multiply it by S. The apostrophe does a transpose, otherwise you can write out transpose. So this is the output of my Y. So all I get to see is X and Y, and I want to recover S exactly here. I can also write this as Y equals X times. That should also work, right? So that's S transpose. Okay, so good. So now S is hidden, and we'll see if I can recover it. Okay, cool. So how do I do this? What was the first thing I needed to do? I need to choose a column of X, which was maximizing. I wanted to somehow take a dot product. A dot product is you multiply 2 vectors. So I'm going to set R equals to Y. Okay, and now R, and then I'm going to look at the dot product of R transpose times X. So this will give me the first column. So if I do this, I get the first column of X. Okay, if I wanted the first row, I would have done this. Okay, and this is the first column, and so this is the dot product of the first column. It's 0. This is probably not going to be my choice, right? If I look at the second column, also 0. Third column, 1. Okay, so far, that's the best explanation. 4 is 2, that's now my best choice. 5, does it keep getting better? So the 5th column, 6th column back down to 1, so 5 is still my best choice. 7, that's good. 8, okay, that might be my choice. 9, that's 4, this is the best so far. And 10 is 0. Okay, so I did all of these. And so if I had a tie, so look, 8 gave me a -3. This is equivalent to 5, which gave me 3. If I had a tie, I guess you pick one arbitrarily. There's no necessarily good explanation for this. Luckily, in this example, I have 4, which is the best. Okay, good. So I think there's going to be a non-zero in entry 9. If any of you remember my original signal matrix, or the original signal vector S, I think that was correct. But let's see. Okay, so now I want to do, so R, so let's do, so let's see, if I do X 9 times 1, right? So let's say I put a 1 bit there. I put a 1 bit in an element. I'm going to get this as my guess of the signal, or of the measurement. R was the measurement. This and this is what my guess was using just the 9th column. Okay, so what happened? I got these two things exactly already. This one, I got part of this one, but I also got this leftover thing in the first entry here. Okay, so I need to update my R is R minus times 1. And if I knew it wasn't 0, 1, I would have had to solve for the value 1, but and so now this is my residual. This is what's left. Okay, so I added something in here, but I now have fewer non-zeros. So this is probably better. The overall norm of this has decreased. So it looks like I'm going the right direction. Yeah.
So times 1 is your gamma?
Yeah, the 1 was the gamma, yeah. If I know it's bits, then I know it has to be 1. If not, I would have had to solve for that. Okay. Okay, so now this was the first round. Now I need to go back and do all of this stuff again, right? I need to go back and check which one of these columns was the most effective. I've updated my residual now, right? I used y was equal to r, now I've updated this. So I checked the first column, still useless. Second column now is doing something. I think it was a 0 before. Column 3 is doing even better. 4, nothing. More of these, I'll skip 6. Even more of these are zeros, so this is good. 8 is now -1. 9 and 10. Okay, so let's go with column 3. Okay, column 3 is the largest norm. And so let's look at this is my guess of this signal from column 3. Let's compare that to R. It's great. I guess, I nailed these two things, but I've added 2 other terms here. Well, at least I'm not making it any worse. But I will take this and so let's see what happens. So R equals R minus X times 1. Okay, now this is my residual. Let's go back. Again, column 1 is useless. Column 2 is telling me something, okay. 3 is -2, but I already, so I'm not sure that's helping. I already chose there. 5, 6. 6 is also 2. 7 is also 2. 8. 9, 10. Okay, so what happens now? I've got a tie. Well, I'm not going to pick column 3 because I just picked that one, and that really didn't do anything. I didn't really explain anything. Let's try. Which one should we try? Let's look at some of these columns. So in general, I would pick them arbitrarily. Let's see what happens. 8. This looks like it's not really that sparse. Let's look at 7 was also a good one. Let's see, what other ones did we? 3, 6, 7, 8. Let's try 6. 6, oh boy, that one looks good. You know, so if we do r minus times 1, oh, shoot. Oh no, I overwrote my r, okay. This is why you should write it in code. Okay, oh no, this is exactly, this didn't change r, it turned out. But r was actually this before, minus 1. Okay, so I didn't actually do anything. Let's do r minus this, okay, which is all zeros. Okay, if you don't think I actually cheated at this step, then you should be amazed that we got the residual down to all zeros, which means that with 3 columns, we exactly explained that signal, right? So we only had was these 10 measurements. I guess we had 10 measurements over 10 bits, so maybe that's not so amazing. But, so we're able to say that, let's look at now x was it 9 times 1 plus x 6 times 1. This was what we got, and this was s. That was the. So if you added those together, then that was the. Let's see. This is the 9th column, the 6th column, and the 3rd column. Right. So s times x should give us exactly this back. So we got our original signal back from just those 3 columns. So, okay, so that's kind of how it works on a small example. So you seem worried that this isn't always going to work. Maybe you have to think that this is like a thing that occurs at scale, and you need kind of a lot of extra readings so that you're going to recover some ones that are kind of like deceiving. You might accidentally pick a wrong column, right? So that's why you needed this extra step where you solve over all of the columns that you saw before. But if it has, you pick a wrong column and you get all the other columns correctly, then at the end you're going to get that column back is going to match as the highest dot product. And so you're going to again be able to put that one out and then just set the bit back to 0 again by saying it should have been a -1 instead of a 1. Okay. So cool. That's pretty much what I wanted to cover today. Any questions about this or about anything else we talked about recently? Yeah.
Just a question on the posters that we're submitting. What will be the format of that? How is that going to work?
Good. So the posters. So yeah, let me pull up this document. No. Okay. I can't get out of here. Okay. So if you look in the PDF for the project, I talked some about it, So I'm very flexible in the format. Well, okay, so there are two things about the format. There's what does the poster look like, and then there's what is the file format. The file format should be, it should ultimately be saved as a PDF. That way, if people have sent like Word documents or PowerPoint slides before, and because of different versions, these sometimes don't display the same way. So print it out to a PDF and then send that in, right? But then, how do you want the poster to look? So the poster should be something that is, so there are two kind of main philosophies about how to make posters. In a lot of biological fields, the common way is that you make the poster so you could leave it there, and it's kind of like a paper. Someone could read the poster, and there's like a big piece of text in the middle of it, right? That's not what we're doing for this class. I don't want people, no one wants to read all that text. Okay, so you should make the poster so that if you're explaining your project to someone, and you have 5 minutes to do so, what sort of visual aids do you want next to you so you can point to them? You can point a picture of your data or a table and say, here's what the data looks like, here's what the interesting aspects are, here's what the results are. Okay? Now there should be some structure to it. You don't just want to be like scribbling on a whiteboard, right? So you try and structure it with the title. So it should have a title and your names on it. And then kind of tell some story with it through pictures and maybe some key points, maybe in bullets. Don't use full sentences. You almost never need to use a full sentence in the poster, right?
How big are they going to be on average? I mean, you might say after grade again.
Yeah, they'll be printed. The department will print the posters. They'll be 2 feet by 3 feet. So 24 by 36. And we can either print them so it's 36 wide and 24 high, or vice versa.
So we submit and you guys actually handle the actual printing?
Correct, yeah. We'll do all the printing for you. You just need to do a PDF. And so as long as it's 2 by 3 ratio, it'll print at the right size. If you use a different ratio, your longest edge will be 36, and the other one will be shorter, and you'll lose some space. Yeah, so it's pretty big. Typically, the rule I give is that look at it on your computer, on your laptop monitor, and if you have to zoom in or squint to read the text is probably too small. Okay. Now, monitor sizes vary a little bit, so there's some variation in that, but you don't want a really small font under it. It'll print just fine, and we'll be able to read it, but we're not going to want to be able to read it. Yeah.
Do you have any suggested templates for a poster?
So, like, no. So like, I have a template I use. I use this Apple-specific program called Omnigraphal. That is probably overkill. Using a PowerPoint slide works fine. And think of making one PowerPoint slide. Now you can set the page setup so it's the right size, or Keynote or whatever, and that's easy to drop in figures, to write short pieces of text. And then there may be some templates online you can find that kind of like put it into like 3 columns often makes sense. I've heard 3 is a good number of columns. Having a big image in the middle is kind of that draws your focus is a good idea. At some point I got like a poster expert to come in and give a presentation. I ran like the poster session for the graduate day, and I got this poster expert. So some of this is from him, but you want to have a title at the top, a big picture which explains really is the main drawing point, and kind of 3 columns that everything fits in somehow are kind of are good things to do. People like 3s for some reason in doing this. And so first set up the columns so that they align. It's probably good to have mainly a white background, because you're going to be a little bit of a white frame around the edge just so it prints, but you can print in color. That's also fine. It's a color printer. So you can have a red background, but don't put like black text on red I will, or me or the TAs or both will look at all the posters and tell you if something is too horrible to print. So we'll do a small filter on these, but try and do your best possible. And you should, and feel free to send me ahead of time or show me a version saying, this is what my poster looks like so far, what should I do? And probably in 30 seconds I can tell you a lot about how to reorganize the poster. Great. Cool, so a lot of fun.